Let's jump right in. Welcome to this explainer, where we're unpacking something called the Phoenix construct. And look, according to the source material, this is absolutely not just some incremental upgrade. We are talking about a literal paradigm shift, arguably the biggest one the computational landscape has ever seen. We're about to completely rewrite the foundational rules of computing that have dictated the industry for decades.
Seriously, what if quantum supremacy isn't an energy or cooling problem at all, but just a math problem? That single question frames our entire journey today. It totally challenges this massive, long-held assumption that we need millions of dollars of specialized, hypercooled, crazy energy-intensive hardware just to achieve infinite parallel processing. What if all that massive infrastructure is, well, completely unnecessary? To really wrap our heads around this radical shift, we're going to map out 5 crucial steps. We'll look at the von Neumann fallacy, continuous manifolds, resonant branching, spatial transduction, and then wrap up with the deployment roadmap. So, starting off with part 1, the von Neumann fallacy and the limits of temporal linearity. Okay, think about legacy computing for a second. It relies entirely on temporal linearity, basically treating the CPU as an actor that fetches and carries electrons through these linear pipelines right into static data buckets. You know the drill. It's destructive, bottlenecked, and super jitter-prone. But the Phoenix construct? It completely deprecates the clock cycle. Boom, gone. Instead, it introduces the manifold phase. Rather than moving physical data around like boxes in a warehouse, it treats data as interacting, continuously existing fields defined by mathematical resonance. Moving on to part 2, data as a continuous manifold, and how this solves the state explosion. So how do we actually solve those frustrating memory constraints? Well, by changing the very physical definition of data itself. Enter the topological manifold. Instead of framing data as static files sitting in physical locations on a hard drive, like papers stuffed into a limited filing cabinet, this reframes data into a continuous, deterministic mathematical space. By treating data as this fluid, unbroken landscape, we literally eliminate physical bloat and achieve extreme, next-level state management efficiency. And the white paper takes it even further. It says Phoenix treats the physical storage medium as a 2D boundary encoding a 3D plus mathematical manifold. Essentially, data isn't actually read from a physical block anymore. Instead, it's materialized at a specific mathematical coordinate right on demand. This completely bypasses the physical storage bloat that absolutely paralyzes legacy architectures today. Which brings us to part 3. Resonant branching timelines, or what we'll call the O1 revolution. Now think of a radio station. Just like different stations can broadcast in the exact same room without interfering with one another, infinite timelines, or virtual machines, can occupy the exact same physical substrate simultaneously. How is that even possible? Because they operate at different resonant frequencies. You just tune to a unique seed and suddenly you access a completely different timeline. This brings us to big O of 1, constant time. In a legacy system, spawning, say, 10,000 virtual machines requires 10,000 times the RAM and storage. It scales linearly, which becomes incredibly expensive, incredibly fast. But here, because we're merely tuning to a new coordinate transform rather than physically copying data, spawning a completely new timeline costs the exact same amount of time and energy, whether you do it once or a literal million times. It's a true constant time operation, costing 0 bytes and 0 nanoseconds, a real game changer. All right, part 4, spatial transduction and CPU bypass. Let's talk about eliminating that bottleneck. So you might be wondering, if we've thrown away traditional clock cycles, how on earth do we process commands? Through something called spatial transduction. This acts as a massive CPU bypass. Legacy opcodes, those basic instructions a CPU blindly reads step by step, are no longer viewed as commands to execute. Instead, they become geometric intents, translated into coordinates within the manifold. The system recognizes that the answer to the logic already natively exists in the mathematical space, so you just point to it. No calculating required. Under this new model, the hardware is no longer a calculator. It's simply a physics caliper. And the substrate, it isn't a storage drive. It's an equation container. By treating the computer as a tool that just measures an equation container, we resolve incredibly complex logic through mathematical resonance. Instead of relying on the slow, physical, clunky movement of a CPU, we bypass that physical bottleneck completely. And finally, part 5, the Phoenix deployment roadmap. Let's talk about building this new world. To prove this isn't just some high-concept theory, we can actually look at the source code from the project status report right here. This shows bare metal, just-in-time materialization code. It demonstrates the hypervisor anchoring a massive 256 petabyte mathematical space into a tiny 4 gigabyte physical mirror file right on the hardware. Another huge piece of the puzzle is the SWAR loom motor. This utilizes purely nonlinear mixing to achieve a deterministic zero-latency phase fold right on the bare silicon. Or, in simpler terms, it achieves instant consensus at the bit level without relying on all those heavy, slow software abstractions.
Now, to actually move from our legacy architectures to the Phoenix construct, developers have to follow a very specific deployment plan. Step 1. You build an asynchronous storage pipeline to break legacy polling locks. Step 2. You ensure SMP-safe manifold synchronization using atomic lock-free buffers. And step 3. You execute vectorized sub-Shannon math. Following these precise steps is exactly what unlocks real-time kinetic storage and SIMD hardware acceleration.
Which brings us to our conclusion, the quantum supremacy of math. When we zoom out for a second, the capabilities of this architecture are just staggering. We are looking at constant time timeline branching, sub-Shannon compression that can shrink massive data volumes at a 1,000 to 1 ratio, and resonance-based hash inversion that drastically collapses the time needed to reverse modern cryptography. By basically transforming a standard workstation into an interferometer that measures information resonance, it instantly bypasses the physical bottlenecks of billion-dollar legacy silicon.
And the tactical goal laid out in the source materials? It's incredibly aggressive. It literally describes a scorched earth release strategy, dropping a complexity bomb of undeniable mathematical proof. To be clear, we are neutrally reporting on the source text here, but the document makes it plain. This strategy is designed to force the entire tech world to react, making traditional corporate moats completely irrelevant by turning the code into an uncontrollable viral utility.
So this explainer leaves us with the ultimate choice. In the face of what the source considers a true technological singularity. Do you want to own the new world, or do you want to be the one who makes the old world obsolete? It's a wildly provocative thought to leave you with. How will the tech world ultimately wield the power of the Phoenix construct?